Good morning, everyone. This is Mike King with Pace Analytical. Welcome. We're going to stay open for a couple more minutes here because we've got a lot of attendees just joining. So bear with us. Good morning. I'm Mike King with the National Sales Director of Pace Specialty Services. Thanks for joining us today. We'll be presenting environmental forensics, and today I have the pleasure of introducing our speaker, Joshua Richards. Josh is a professional geologist, a certified hazardous materials manager, and is the program manager for Pace Analytical Energy Services. Pace Energy Services was formed in 2013 through Pace's acquisitions of Microseeps and Zymax Forensics. Josh is responsible for the technical sales and marketing efforts of Pace Energy and comes to this position well prepared by 8 years of experience as an assessment remediation geologist in the consulting industry, working on large-scale remediation projects. Prior to his current role with Pace, Josh gained more in-depth analytical laboratory experience representing Pace Analytical as an account executive throughout the Midwest. Josh received his BA in geology from Indiana University, Purdue University at Indianapolis, and his MS in geology from the University of Florida. Josh will be speaking today on environmental forensics and chemical fingerprinting, so please welcome Josh Richards.
Good morning, good afternoon to everybody. Thank you for attending the national webinar for environmental forensics. Thank you for the introduction, Mike. What we're going to bring to you today is a comprehensive presentation on the environmental forensics industry and how it can be useful in understanding complex sites and complex projects to unmuddy the water, if you will, and make sure all evaluation is present. So who are we? Pace Analytical is a full-service environmental laboratory network with 34 locations nationwide. As Mike stated in the introduction, Pace Energy was created from the acquisitions of Microseeps and Zymax Forensics in 2013 and combined it as Pace Energy. We share a laboratory in Pittsburgh, Pennsylvania, the old Microseeps location. And Pace Analytical with Pace Energy specializes in environmental forensics, and I'll elaborate on that when we get to the persistent organic pollutants. This presentation is going to include insight in petroleum forensics, chlorinated solvents forensics, persistent organic pollutant forensics, and compound-specific isotope analysis. So as with any presentation, we want to give a guideline of what we're going to talk about today. We're going to discuss what are environmental forensics, where and why clients need these forensics capabilities, some of the forensic tools available to our clients, how to apply these forensic tools. We'll go through a few case studies reviewed to detail multiple subject matter that we discussed on the previous slides, and then we'll come back around with a forensic summary. So the definition in layman's term for environmental forensics is an application where there's a dispute regarding an accidental or routine release of a harmful contaminants in the environment. What we see is obviously the market has to have a need to be able to facilitate the analysis and complex problems in these sites that we're evaluating. For the environmental forensic investigation, 5 questions that we're looking to answer are: what are the contaminants? What is the source? When did the release occur? Who is responsible? And then where the rubber meets the road, or the cost-benefit analysis, is how can the cost be reasonably apportioned? The findings should be supported by the data and be defensible in litigation cases. And the important part is to make sure that the data, that's the foundation of the analytical data, is that you're prepared to go into a defensible situation to establish the 5 answers to the 5 questions listed above. So what we see, the market for environmental forensics pops up in 3 or 4 scenarios. We see the apportionment in the Superfund or hazardous waste site, site investigation for property transfer to make sure that the up and coming property owner, potential property owner, doesn't necessarily have to inherit environmental issues that are existing. We see an uptick in the insurance litigation, just like industrial clients, insurance clients are looking to protect their investment for the insurance policy that's there. And then toxic tort litigation that we see from time to time, that, you know, the Aaron Brockovich stories, these civil action suits where impacts have affected communities or the human health, and this is a line of evidence that goes to support or refute claims of contamination. So forensics investigations are multifaceted and complicated. There's a lot of things that go into it to make sure we have a thorough understanding of what's going on. First is to have a good, overall understanding of the site and the conceptual site model. The second, historical data on both the site usage and related insurance coverage. The related insurance coverage, which could expand the capabilities and analytical testing that you could do to uncover some additional analytical information that could go into the overall conceptual site model and fill in data gaps. Fate and transport information on the contaminants of concern. This is key for on a number of avenues. One being to understand where it's going to go, understand what's going to happen to it along that transport, but also be able to signify if it has already traveled, that we can identify the previous information on the material prior to degradation and weathering. Statistical modeling or correlations can assist in contaminant identification. We see this a lot within the POPs environmental forensics area. Looking at principal component analysis. We can also extract forensic information from your existing site data, looking at concentrations, looking at groundwater flow, spatial recognition between sample points. All these go into what we call the multiple lines of evidence. By standalone, environmental forensics isn't the solution to a complex site if other work hasn't already been accomplished. We see a lot of clients come in to request our services or our expertise based on things like inconsistent concentrations or the head scratching of the data that's already there. Something just doesn't make sense, so we have to go another order of magnification into the data and analysis to understand what we can find. We can look at also weathering patterns of high resolution site characterization data, pattern recognition to identify contaminant sources. That's the fingerprint, chemical fingerprint, or isotopic fingerprint. Either way, we'd look at pattern recognition. Then specialized forensic tools can provide the multiple lines of evidence, as I spoke before. A detailed investigation can involve some or all of these tools to assemble a coherent logical argument supported by these lines of evidence that will stand up to the scrutiny of the court. So we'll talk a little bit, we'll start to dive into some of the forensic tools available. First off, we're looking at the petroleum forensics analysis. We approach this in a tiered approach. In each one of these tools, we're going to go into further detail in the upcoming slides. The chlorinated forensics, we're looking at source determination. And then the POPs forensics, we're looking at complex chemical signatures that are the fingerprints of the contamination. So with the petroleum forensics, this is a list of the tiered approaches that we look at for unknown NAPL, L-NAPL, D-NAPL, and in situ. We start with the whole oil analysis. If there's not much historical information about the site, this is where we're going to be able to determine the petroleum hydrocarbon types that are present, as well as the potential to identify some chlorinated solvent through a tentatively identified compound off the mass spec run. The tier 2 is where we start getting into such as like a flow chart. The tier 1 is to identify unknown, but it's like the 25,000 foot view of the analysis. From there, we can make analytical decisions of what direction we want to go. So we get into the tier 2, and you'll see that the second and third bullet are both tier 2. If we see a majority of the contamination in the whole oil analysis is in the gasoline range, then we can provide piano analysis to look deeper in. And I'll go into a little bit more detail about that in the upcoming slides. If we find that it's more of the middle to heavy oil distillates, then we implement a full scan analysis. And we can look at some of the longer hydrocarbon chains for petroleum fingerprint signature. Then tier 3, once if we're out of the second tier and we're looking to differentiate sources, we're going to look at the CSI dissolved phase petroleum VOCs on particular compounds. I'll get a little bit more into the CSIA and its importance and structure in a few slides. So back to the whole oil analysis, it's a GCFID screen. It identifies up to 149 compounds. And then, like I said, it identifies general petroleum types. Once we've done that and we kind of have a realm to work in, and then we identify that this is a gasoline range impact, we look at the piano analysis, which gives us a C3 to C12 range. It quantifies 120 compounds. And this is more of it adds diagnostic and biomarkers into it. This is, as I referred to the whole oil as a 25,000 foot view, we can look at the quantitative gas range fingerprinting and full scan as more of a 5,000, 10,000 foot view, where we're a lot closer. We can see a lot more detail and start making some determinations. This is a key component for starting our conversation for data for plume aging and source identification. In the top right corner, this is a standard star diagram for piano analysis based on their relative percentage to each other. And you can see that there's 5 samples that are listed here, and you can start to see some overlap. This is just an example from a previous case study, but to start introducing some of how the data is represented is key to understand how we can determine different sources. Some of the other items that we can use within the gasoline footprint is 2 additional type of analysis that can give us data useful for aging and sourcing. The first one's the oxygenated blending agents, such as MTBE and ethanol, an additional 4 oxygenates. And what this does is this further defines the petroleum fingerprint for that sample. As petroleum refinement has changed and different manufacturers add their recipe, we can differentiate between samples utilizing that analysis. The other, and this shouldn't be too big of a surprise, is quantifying EDB and organic lead concentration. Again, as petroleum refinement has changed, we have a couple significant error points in time that are significant in the lead concentration of gasoline. Utilizing those and also the 5 alkali lead compound additives really gives us the ability to start constraining age of release. So that wraps up the piano analysis and a couple of analysis that go along with that are useful for age dating. The second part is the middle to heavy distillates. And I want to put on hold real quick. I forgot to say at the beginning, if you have any questions as I'm going through this, please submit them in the chat and we'll answer them at the end. If we have a high quantity of questions at the end, then we'll just pick ones that are more comprehensive or pull out a particular detail that might be beneficial for everyone. The ones that don't get answered, we're going to follow up via email or phone call later on. Sorry for the interruption, but that forgot to mention that at the start. Back to the full scan analysis for middle to heavy distillates. This is a full scan analysis covering C8 to C40, using distribution of alkanes, PAHs, etc. This is really beneficial in characterizing diesel, kerosene, crude, heating oil, lubricating oil, such like that. And as you can see, there's a similar star diagram in the lower left that's useful for full scan analysis in comparing diesel samples. You can see there's many more proponents that go in it. Again, we see 5 samples that are very similar in percentages. On the right, these same set of samples are then plotted in ratios for certain biomarkers within the sample. And you can start distinguishing differentiated groups, as well as we added some archive data for diesel releases to kind of give it a comparison and show how the ranges can vary and how you can group samples accordingly. And then coming soon at Pace Analytical Energy Services that already exist in Pace Minneapolis is the Parentalkylated PAHs. We're currently subcontracting the petroleum aspect, but we're bringing it online and should have it online in first quarter of next year. Useful for higher resolution results. It's used on MGP refineries, complex sites where there was a refined crude, but not all the way into the light to middle distillates. As you can see right here, even analyzing the PAHs in a gasoline and crude petroleum, you can see a distinct fingerprint that could be useful for if you have multiple samples. Plotting just the PAHs can give you significant information of mixtures, of what kind of refinement it's also been through, and be able to differentiate sources if the data allows. So that's the summary of what capabilities are in the marketplace for petroleum forensics, from looking at a whole oil to try to determine what the unknown characterization is, to looking at piano analysis for gasoline impacts, really looking at the biomarkers and other diagnostic information within it, then looking at middle and heavy distillates to also look at biomarkers and diagnostic information that's within it, and being able to differentiate between releases of petroleum, releases of diesel, releases of both, separating them out, finding complex mixtures, things like that. So with the chlorinated forensics aspect, it's a little bit different. Characterization can be accomplished by EPA method 8260. A majority of the 62 compounds that are within that EPA method mainly deal with the chlorinated solvents. For the petroleum aspects, significantly, it's just BTEX. So it's really hard to distinguish between releases and petroleum impacts based on BTEX only. For the chlorinated solvents, although it will be diluted for NAPL, you can get some information about what the main contaminant is based on the 8260 data you receive. So utilizing chlorinated forensics, we have to look at a different way to give that individual fingerprint to a known source, and that's the compound-specific isotope analysis. It's a multi-use tool for chlorinated compound forensics, as well as petroleum forensics, and I'll show you that when I go through the current market of CSIA. The use is a degradation of daughter products, making sure that your remediation plan's in good shape by understanding the change in isotopic ratios. I'll describe a little bit more about that in the upcoming slides. You can also look at commingled contaminants, same or different source, and then also weathered product from original isotope signature. So I know with the diverse amount of people that we have on the call and that I've talked to in my time as the program manager, everybody comes with a little bit different understanding with what stable isotope analysis is. Some come from an academic chemist background. Myself as a geologist, I dealt with stable isotopes in my graduate studies. So I wanted to go through just a couple slides to give anybody on the call that's not familiar with stable isotopes a little better understanding. The molecule is the same number in protons and electrons, but comprised of a different number of neutrons. For the example that we've done here is the most abundant stable isotope that we utilize in CSIA now is carbon. So you can see the stable isotope at carbon-12 has 6 neutrons, atomic mass of 12, bond strength's weaker relative to carbon-13, and its relative abundance is very, very high. For carbon-13, both of these are stable isotopes. Carbon-13 has 7 neutrons, atomic mass of 13, stronger relative to carbon-12, and its relatively lower abundance makes it easier to separate. The light isotopes, because the bond strength is weaker, degrade more rapidly. The product remaining, and product is just the impact, the dissolved concentrate, or whatever the product, not necessarily meaning apple, becomes isotopically heavier. The process is called fractionation. So what we're measuring is just the degradation or fractionation of the faster breaking bond strength of carbon-12 relative to carbon-13. This is a diagram that I use in my webinars now that I saw in college as well. But this is the picturesque viewpoint, if you will, of what we show as degradation within a sample. The far left beaker with yellow and blue candies is the, say, undegraded product, the T0 sample. As you move left to right on the page, you can see that there's a change in relative percentage of blue and yellow candies. If the blue represents the carbon-12 and the yellow represents the carbon-13, as degradation occurs, and I say degradation in the sense of naturally occurring, in the sense of passive attenuation, or if it's stimulated via bioremediation, bioaugmentation, biostimulation, the rates change. But as degradation occurs, what we see with the carbon-12's bond strength being weaker, it falls out faster, degrades faster than the carbon-13. Relatively from left to right, the abundance of carbon-13 versus the carbon-12 increases, therefore making it isotopically heavier. And that's where we prove degradation. Here's an example plot of CSIA for PCE, looking at two-dimensional. We call this two-dimensional because two isotopic concentrations were used. For on the bottom is the delta 13 carbon, which is carbon-13 over carbon-12, and on the y-axis is chlorine with delta 37 chlorine over delta 35 chlorine. So with these, we're plotting the ratios of each. As you can see in the big green arrow in the middle of the graph, degradation is generally in that direction to the upper right, because both ratios are going to become more positive over time as the numerator, which is the heavier of the two stable isotopes, increases relative to the denominator. So as you can see, this is without additional information, we would define this as a couple different sources. We have the red box labeled as B and the blue diamond representative A. The CSIA is a presentation that's standalone, but I want to give you guys some information, also show you how the data is plotted. By looking at this in the relationship spatially, as well as the analytical data that's produced through the analysis, we can see two different pairs of groupings. Case study later on, we'll go a little bit more in depth. A useful CSIA document that I refer to on a regular basis and refer clients to as well was written by the EPA. The link's at the bottom, but really if you just type in US EPA CSIA, this document link's going to come up. It's really well written. It shows a fundamental understanding and talks a little bit in complex studies of how to utilize this data and some of the pitfalls that go along with it. So what I wanted to talk about next was what really means a lot for you guys is what market do we see CSIA functioning in right now? As I said before, carbon isotopes are useful for establishing evidence of degradation versus dilution. So as your concentrations go down, that could be from dilution and not necessarily from degradation. CSIA can help understand what the process is going on. It can also measure the fraction of compound degraded, and with the right sampling plan can give you a rate of degradation. That's called one-dimensional when you only have one isotope being used. The next set of bullets is a carbon and chlorine. That's a two-dimensional analysis. That's really where you start to see the XY plot, as I shown on the slide before. And that gives you the forensic evidence for multiple sources of chlorinated solvents. And it also still provides degradation information as well. The carbon and hydrogen two-dimensional isotope pair has a few different applications. It provides degradation, as they all do, and forensic evidence for petroleum impacts. Obviously, since there's no chlorine in petroleum impacts, can't utilize chlorine isotope, so we can utilize hydrogen isotope to look at BTEX, naphthalene, additional compounds, as well as utilizing CSIA for piano analysis. We can also utilize carbon and hydrogen for 1,4-dioxane for those who have sites that are being evaluated for that because of chlorinated solvent impacts. It can be very useful to understand, identify additional sources. Additionally, with carbon and hydrogen, and I think this is why we have the Pace Energy label when that acquisition came about, was right around the high point for the Utica and Marcellus shale investigations and the need for methane speciation. Utilizing carbon and hydrogen, we can look at methane from a shallow or deep source, methane from landfill, background, pipeline, other natural sources. It's very useful analysis in understanding what impacts are responsible from the source or what could just potentially be background. Additionally, with comparison of background is the nitrogen and oxygen pairing, where we can look at nitrogen from nitrates from confined animal feed operations, wastewater treatment plants, or land applied fertilizers to differentiate between anthropogenically sourced material, background, runoff, anything like that, and kind of differentiate between the source and what's responsible. So as I mentioned, with a proper sampling plan for CSIA to prove rate of degradation, here's just an example slide of what you can evaluate and think about when you're wanting to implement your CSIA program. It's, for instance, if you take a NAPL sample, you take 3 samples from each plume, you can look at the carbon CSI results to try to figure out the degradation for if the NAPL is a chlorinated solvent, looking at carbon and chlorine. If you see no differences, that's where that secondary dimension could work out. With that secondary dimension, looking at partition into groups, most likely they're going to come from different sources. However, as I stated a couple times already, this is part of a multiple lines of evidence. We're going to need additional information that you'll probably already have to evaluate the spatial relationship, the vertical and horizontal relationship, the groundwater concentrations, the geology, the hydraulic flow, anything like that can come in. So if you have same but conflict with the CSM, the conceptual site model, it's funny as to say just revise your conceptual site model, but take that in as your data gaps and try to figure out if there's an undiscovered source, or you start evaluating what's going on. If most samples are different, you could indicate multiple spills, and then we can treat one of those individually and try to find out some more information. So for the chlorinated forensics, we utilize CSIA to have a better understanding of proving degradation or trying to find differentiate sources by a two-dimensional analysis. But as you saw in my current market slides, there's other uses for CSIA for environmental forensics, such as the nitrate aspect. One I didn't mention was the oxygen and hydrogen that can be useful in providing a fingerprint for surface water, groundwater, confined aquifers, unconfined, and finding the relationships between each. So there's a lot of useful ways to push CSIA into your project if you're needing to gain some additional information. So with another leg of the environmental forensics is the persistent organic pollutant forensics, known as POPs. So our POPs lab is in our corporate headquarters in Minneapolis, where we can run the dioxins and furans, PFAS, PCB, congeners, and utilize or bring those analytical tests to the forefront to have a better understanding of impacts. So really with the POPs labs and POPs forensics, we're looking for pattern recognition. Fingerprints, like looking at homolog and congener patterns for PCBs, patterns associated with known sources, fate and transport impact on pattern degradation, as well as biomonitoring of plants and animals through, fish tissue, sediment, things like that to give a better understanding of exactly what's going on. This can be useful in PAHs, PCBs, DOCs, and furans and PFAS. They're made up of multiple components, and sometimes this is assigned toxicities that often exhibit characteristic patterns. By looking at the toxicity calculations, you can understand what's most impactful and harmful. This is just an example of looking at different signatures for a petrogenic and a pyrogenic alkali carbons. You can see the weighted percentages. The relative abundance is on the front end for the pyrogenic, where it's a nice statistical array for the petrogenic. So what I'd like to do is go through a few of our case studies, and a couple of the case studies go deeper into the POPs forensics, but I wanted to do an introduction there before we get into the higher level, looking at the data and the project specific information. So for the first one, we're going to talk about chlorinated CSIA. This is a case study. We did some work at Industrial Park in North Carolina. It's a degreasing operation. There was chlorinated solvent impacts that were, we'll call them Company A, that operated the degreaser. There was a solvent plume that was moving down gradient, had crossed the property line, and the client acknowledged the responsibility, but there were some vapor intrusion concerns that arose in a mid-property offsite, but the second property down gradient from theirs, and later converted in private homes off-site as well. So you can immediately, just by those two statements, the environmental responsibility escalated pretty quickly. Company A's consultant suggested CSI evaluation to determine if an alternate source existed. There were a couple of possibilities. We were able to run carbon and chlorine, two-dimensional CSI in multiple wells moving down the plume and near the property line to see if we could find a unique isotope signature that might indicate another source. What we saw dissolved concentrations inconsistent both vertically and horizontally. So there's the term that makes you try to think outside the box. Concentrations weren't making sense in both the X and the Y direction in the subsurface. So you're going to have to expand your capabilities and take a look at what you can find. The figure on the right is the site figure, or the orange polygon in the top right corner is a client A or company A. Their impacts were in the bottom right-hand corner of the site for PC and TC detections. The center building, or the building in the center of the figure, is the one that vapor intrusion had begun. And then you can see the residential properties at the very southern end, southwestern end of the figure that shows the residential properties. As you can see on the left, this is the data that from the wells. I know it's a little bit hard to see, but the yellow boxes on the figure are the relative, are the number, the reporting number for the carbon or chlorine analysis. You can see, if you can see it very clearly, it's in the negative part. So as you can see on the left-hand side, this is the data for 31 wells. Some of them had PC and TC, but some of them were based on the spatial aspect and the concentrations. Not all of them got both analysis. So what you can take a look at is the carbons on the x-axis, the chlorine isotopic ratios on the y-axis. And what we were able to do is take a look at a couple different trends that we saw. As you can see, the filled-in triangles are PCE. We were able to attach a best fit line for two distinct patterns. And then the hollowed out triangles are the TCE. One of the questions at the site was, were we able to determine PCE or TCE's existence as it was lost directly, such as it was purchased and utilized as TCE, and differentiate between the TCE as a purchased material or as a daughter product of the breakdown of TCE, excuse me, of PCE. And the relationship and conversation with our technical experts can go into how the best fit lines and how our summary and conclusions can come about. But looking at this in the relationship of degradation, the TCE was determined it did not come from the PCE as it's degraded on a different path. So the ratios are changing at a different slope than what we saw with the two identified sources on the left. And what this did for the client is Company C, which is the middle building, was also contributing to the plume. Company A was able to offload a portion of the cleanup costs by identifying these sources and utilize them in a spatial relationship to understand where those differences were at. The cost benefit analysis in CSIA study was around $60,000 with 31 samples of two-dimensional CSIA analysis with interpretive reporting, and client saving close to $500,000 in cleanup. So if you can differentiate between your impacts on site and off site, especially as it gets to the residential area, and either a portion or relieve yourself of the cost, you can see obviously that the return on investment of $60,000 for a $500,000 savings is significant enough to utilize this information to understand responsibility as well as the contaminant properties. So looking at, this is kind of a two-tiered approach. It really toes into the CSIA, but PAH evaluation was done as well. We had a pipeline spill. We did not, excuse me, our client had a pipeline spill near Santa Barbara, California. 3,000 barrels of crude oil on coast and into the Pacific were released. 7 miles of coastline were impacted, including 4 state beaches. And tar balls were reported on beaches 100 miles south of pipeline location. The next figure shows shows a map of where everything occurred. So in the middle, where it says Refugo State Beach closed 5/19/15, that's where the pipeline break was at. You can see that up and down, when you have your near shore current and your long shore current are basically moving the water in opposite directions, you can get transportation of this material up and down the coast. This is also a busy oil exploration and a transportation area. The pipeline served active oil platforms as well as, platforms off the coast, as well as it's a coastal ship traffic, and an active seep is in the area. So by looking at that in a vacuum, you can see there's coastal ship traffic, there's a pipeline that's feeding the platform where they're drilling, so there's drilling operations, there's a seep, and just anthropogenic causes as well. You can identify 2 to 3 different sources. So what our client asked us to do once the cleanup was underway was to take a look at the samples. The main pinch point was the tar ball effect. Because of the vastness of the impacts, the capital expenditure needed to clean those up was significant. So then you start evaluating what can we spend to make sure this is ours. It's not about trying to push the blame, it's just trying to make sure that it's yours or not. So Pace Analytical handled most of the laboratory work in support of the emergency response and cleanup. And a portion of this work included an environmental forensics investigation to fingerprint the crude oil from the spill and the other background sources in the area, including the active platforms, the active seep, which was collected by divers. So we're trying to differentiate the sources of ship traffic bilge water, the seep, and platforms. So collecting samples for CSIA proved very helpful for this. First off, we tested hundreds of samples by the light distillate and residual range scan. They established a clear fingerprint for the released crude. The fingerprint was used as a comparison against claims to determine if the claim material was from the release. Although some litigation is still outstanding, the client estimates savings in the millions due to the avoidance of cleanup activities for claims that they were able to prove were not related to this release. So the tar balls are part of the active seep, but by putting a chemical fingerprint to those samples, the platform samples, the pipeline samples, and any that were collected as bilge traffic, you can start seeing some differentiation that the person responsible for the pipeline breach isn't responsible for all the cleanup. So here's a case study for the POPs Forensics Lab. What we had here was a pulp mill paper and pulp mill became the target of suspicions that their stack emissions, which were known to include trace levels of dioxin and furans, were negatively impacted downrange receptors, specifically private homes that employed rooftop collection systems to capture rainwater in cisterns. And they're determined trace dioxin and furan in the drinking water. The paper mill had studies which indicated the homes in question were outside the stack's deposition zone, and therefore unlikely to be receiving those types of contaminants from their emission. So I want to take those couple statements and say, here's an example of understanding the site prior to utilization of forensic analysis, without them understanding where their stack's deposition zone was, what clear downwind channels are. They're going to have a harder argument to say that's not ours or that is ours. So by having that in place as part of your management plan that exists, this is an industry example, but if you look at it as your site management plans, you're going to have additional information that kind of helps roll out the CSM and kind of fills in some data. The paper company knew the congener pattern of the emissions from regular testing, and that's equivalent to groundwater concentrations at a petroleum site or chlorinated site. They were able to factor in the impacts of fate and transport, would have that on the congener pattern. So as the congeners break down, we can still find forensic information within those. Samples were taken from the forest floor directly downrange of the paper mill in the known deposition zone. So they have a potential source that's moved, but they understand where it's at. So evaluating the congener pattern from the cistern samples was markedly different from either the stack emissions prior or the deposition zone pattern. Now we'll say with the POPs forensics, a lot of the time, or I should say a majority of the time, the secondary analysis, the data analysis is handled by clients. So we don't always have information or charts or graphs that utilize that. So this was pulled off out of a paper in 2004. This just shows you utilization of the 17 dioxin and furan congener patterns can indicate here's 7 sources. They look pretty significantly linked from the same source, so to speak. And these are for air emissions. So you can see the OCDD is the major contributor to the amount of impacts present, but you're not really relying on the 2378 TCDD, which is the heaviest weighted by toxicity calculation for the dioxins and furans. So using those chemical fingerprints is useful for this company to understand and identify that they're not at fault for the examples or for the concentrations that existed in the cistern samples. Doesn't necessarily analyze for what is, but it can give you a second look to try to find different sources that are affecting that receptor. So the next case study was in regards to a pipeline spill, excuse me, in the Kalamazoo River. Estimated that 1 million gallons of diluted bitumen was released in the Kalamazoo River. The spill was not contained until a 35-mile stretch of river and floodplain had been impacted and subsequently remained closed for nearly 2 years. The eventual cleanup costs were around $1.2 billion. This is the largest inland river cleanup in the history of the United States. And so utilization of forensic analysis, specifically the PAH, because it's the higher end distillates, it's basically the glue for asphalt is what the materials is utilized for mostly. But doing a forensics fingerprint of the spill will allow for a better understanding of exactly what signatures are present in the river. So the overall cleanup was complicated by the fact that dilbit, which is short for the diluted bitumen, initially floats like any crude oil, but as the products are taken out, it then sinks to the bottom, necessitating a dredge cleanup. Because the Kalamazoo had been an active commercial river for over 100 years, the responsible party undertook forensic investigation to determine the extent of the present spill and makeup of the existing background contaminants. The investigation was able to accurately delineate the spill, and although the remediation activities clearly had a positive impact on the entire area of the cleanup, including the removal of historical contamination, the forensics investigation was successful in saving the responsible party significant sums of money that might have been spent cleaning up areas and the current spill did not impact, for which they're not responsible. And so utilization of forensic analysis after the spill had occurred, routine sampling had occurred to identify impacts, but not specific enough to understand which impacts were tied to that release. Utilization of the forensic aspect is what is allowed for a higher resolution understanding of the impacts to provide for the main PRP to facilitate cleanup, but not outside the realm of their responsibility. And then once that fingerprint's established, it can be utilized to understand where potentially other sources were, if the information's already out there. So with the case studies that we just went through, I wanted to bring the environmental forensics summary. We're looking as environmental forensics is an expanding field. As remediation projects and sites become more complicated, we need higher level analytical capabilities to differentiate, assign fingerprints, understand sample interaction, but it's all driven by risk and liability. As the risk increases and the liability increases, these tools are useful to unmuddy the water to understand the exact history of a sample. So solutions are needed for environmental disputes. As professional in forensics investigation will involve a complete site understanding facilitated by you, our client, the use of historical data and statistical analysis. A lot of the POPs forensics uses statistical analysis to understand probability of these. For instance, PCB congeners, there's a list of 209. So utilizing that information of the 209 congeners can be significant in understanding the fingerprint of that sample. Thoughtful application of the forensic tools that I just reviewed, petroleum, chlorinated solvent, CSIA, POPs forensics is obviously key to understand that we have the right one. And a successful outcome will require defensible data that will stand up in court, and also multiple lines of evidence to support the claim. So with that, taking a look at some of the questions that were presented, we can go into that. Here's my contact information. I did put the Pace Energy Services address and website up. As I said, the POPs forensics and the alkylated PAH is currently out of our Minneapolis lab. But if you have any questions regarding that specifically, I can forward the information over to our program manager, my colleague, Nathan Eklund, who is involved with that laboratory. Excuse me. So with that, I'll get to some of the questions. I have one that, can you please confirm whether your piano analysis is fully quantitative or semi-quantitative? Is the data reported indicative of percent amount of oil or water vapor concentration? With that, our analysis is semi-quantitative. We're working on pushing that to fully quantitative, but I don't have a timetable on that. But what we can do is we can, obviously with the GCMS scan, you get time on machine versus peak intensity, and looking at the impacts and how high their peaks are gives you the understanding of what impacts are present. But with that, we can do percent amount. With the oil or water vapor concentration, that's a little bit more specific. When we do the whole oil, we're talking for Hoyle example, the 149 reported compounds, we're looking at NAPL only. But when we get to the piano and full scan, we have the capability of doing soil, water, and NAPL as well. Is this PowerPoint going to be available after the talk so I can share with my colleagues? I can make that available. Have your name, I can present that. It'll also be, it's being recorded right now and will be able to be watched at any time. So if you don't want to pass it on, you know how presentations are. If you give somebody a PowerPoint, they're missing a lot of the information. You can tune them into the recording and they can listen to the presentation we just went through. Next question, but what if the sources all purchase the solvent from the same supplier in the same time frame? This is a great question. And in the CSI standalone presentation, we actually go through the differentiation of sources. I have a figure in a previous presentation that talks about the lot, say a lot number from, you know, if you're talking about TCE or TCA that Dow or DuPont or another manufacturer put together. The probability that, so if we bring this into a realm of multiple sources, let's assume that the secondary sources off-site, we would have to have them buy the same lot number from the same manufacturer location. Just as most distribution of product, they have regional locations where material is either made or shipped to direct. If the material is all made in one location, same lot, at the same time, instilled at the same time, you know, purchased to the end user, and has to be spilt at the same time, I would say that there would be difficulties. But because the site geology, the site hydrogeology, the time of release would all change the degradation pattern. It may be very, very slight, but looking at that, if you have that information up front, we may say this may be difficult to determine if all those things happen to fall in line, which is highly unlikely, but if they all fell in line, we might just have to come to the conclusion that CSIA may not be functional for determining PRP involvement or responsibility for multiple sources. But as I went through that list, you can see purchasing the same lot from the same manufacturer at the same time, spilling it at the same time, and then all the characteristics of the site are similar. We could see some difficulties in interpretation, but we don't really understand the interpretation until obviously the data comes out and we can take a look at it. So if you have inconsistent concentrations at the site, both horizontally and vertically, or one or the other, that may be a differentiator enough to prove that, okay, we see the CSIA is not a standalone product, but the multiple lines of evidence, it could be helpful and indicative that even with all those conditions met, you could see some differentiation. What if you don't have a product sample? What concentration levels provide useful results? That's a great question. Luckily, we don't always have to have product samples. They are helpful. As it was told to me a few years back, product allows you, if you're looking at a book, that you have the cover, the table of contents, the chapters, and some verbiage within that. So the story is really strong. With dissolved or soil, you know, the story changes a little bit, but utilizing other parts of your CSM can fill that in. So with dissolved samples, you may not have the cover or the table of contents, or you may have one or the other. You may have chapter headings and a lot of text, or no chapter headings and some kind of intermix. Hopefully that analogy worked. But with dissolved stage impacts, we're looking at 5 micrograms per liter for most of the compounds, but each compound for CSIA changes based on detection. But we are working on reducing that, and we feel comfortable with getting down to 2 to 3 minimum concentration limits for CSIA. But it all depends on the compound, and that all gets established with a better understanding of your site with a upfront free consultation about your project to see if CSIA would be beneficial to answer your project objectives. So we welcome the conversations to discuss your site and find out how we can help you with any of the environmental forensics. What if you, excuse me, do you use the alkylated PAHs and biomarker ratios for the Santa Barbara project to support your findings along with CSIA? We did not utilize CSIA on that project. We used the comprehensive full scan. And I got a note here to make sure I had that all right. So we use the ASTM D5739, the light distillate to residual range ECMS scan to establish a clear fingerprint on the released crude. And with that, there's the biomarkers and the PAHs are present. It's just not a specific analysis like the alkylated PAHs specifically. So we were able to use that to identify that. In that case, it would be a chemical fingerprint of each source to show differentiation. And then the argument that comes of, you know, you could say the tar balls or the active seep is an undegraded product where the crude, even if it hasn't went through much refinement, has been exposed to some sort of processes to refine it. I'm not a crude oil expert, but that's just kind of what I pulled together from past experiences. Okay, that wrapped up the question. Actually, here's another one. By petroleum forensics testing, can you differentiate an older production water spill and a new spill from the same well? That's a good question as well. Yes, and that's one of the parts of the petroleum forensics that I discuss with, you know, on a one-on-one basis, in the sense that it's petroleum forensics is even useful for detecting releases from the same tank with the same type of product, whether it's gasoline, diesel, over time, even if you're not looking for additional PRP or there's no property transaction. I know some states will extend the cap, the remediation cap for the site, if you can prove another release occurred while you were remediating the first one. It's very specific, but we've seen some success with clients in how they look at releases and spills, and the usefulness of being able to determine the fingerprint based on that. Another question came in. Are there any case studies involving POPs forensics of PFAS contaminations? Currently, we don't have any that we can put on the presentation. The case studies, unfortunately, take a while to pull together. That is going to be a significant field that's going to expand. As you all know, the uncertainty of where PFAS is going. I mean, I guess we know where it's going. We don't know how fast and exactly what direction it's going. But what we're seeing is that it has a complex chemical signature. So as we gain more understanding, we will be able to implement those pattern recognition and forensic tools to identify, or I should say separate, samples if they're coming from different sources. One question I get a lot is, can you do CSIA on PFAS? And unfortunately, the answer is no. I don't know if there's any realm that it's going to happen, mainly because the fluorine carbon bond is one of the strongest in nature and therefore difficult to break. And then also analyze at that concentration, as you notice that the most PFAS is in the PPT range. Next question is, what isotopic analysis exists for metals to determine the source of coal ash contamination? That's a good question. That's a little bit out of my realm, but as a consultant previously, the only thing that we were able to utilize is speciation. So speciation of mercury, speciation of arsenic. I know that we do get a request every once in a while for boron isotope analysis, which we don't do, and unfortunately we haven't been able to find a subcontractor for that. But I know that was tied directly into the coal ash, the CCR rule, with moving ash piles and trying to determine release or impacts or anything like that based on the concentrations of specific elements or metals within that. So unfortunately, we don't have a forensic aspect for that, but I have been successful in closing a few sites in my previous days utilizing speciation of metals, specifically arsenic. And then is there a prescribed method for CSIA, ASTM, or EPA? Not specifically. Looking at how we analyze on the IRMS methodology exists for detailing the samples, but from my knowledge, there's not an ASTM or an EPA method associated with it. I could be mistaken, but from my understanding right now, there's not. I can follow up with some additional information, but that US EPA CSIA guide goes through all that aspect from the EPA's eyes. And one realm that we work with in forensics is a majority of this is not regulated. So you're not going to find that the regulator forces you to. However, I've done persistent organic pollutant forensics at a couple Superfund sites when I was a consultant, and it was a directive. I guess it was a joint venture between the PRPs and the EPA. So they wanted to kind of do it, but they didn't know enough about how to do it. So we provided the information. We tackled it as a team, if you will, to have a better understanding. That was a PCB site. Okay, well, I think we've answered all the questions. Appreciate you guys taking your time today to listen about environmental forensics and how Pace Analytical and Pace Analytical Energy Services can be your provider for the analysis that goes into this understanding, this market. If you have any questions, specific to the presentation, want to talk about any projects that you guys have, my contact information is on the front, or if I need to redirect you to the POPS Forensics Program Manager, I can do that as well. And if the few more questions that we have, we will answer in writing, but since we're right at about an hour, we'll go ahead and end the webinar now. So thank you very much, and stay tuned for more additional webinars that are to be coming out for Pace Analytical on different topics. Have a great day, everybody.